Hello, thank you everybody for being here. This is eBPF ELFs jumping through the windows. And I am Richard Johnson, senior researcher at Trellix, part of Trellix Lab. And before I get started, I just quickly want to give a shout out to our teammates, Kashmir and Andrea, brilliant interns that I've had the pleasure to work with and contributed to this talk and implementing some of the fuzzing harnesses. So today we're going to talk about what is eBPF in general, what are the origins and applications of this technology stack. And this talk in particular is going to be focusing on a new implementation of eBPF that's now coming to the Windows platform. And so we'll be doing a deep dive into the APIs and attack surfaces that are available to security review. And then we'll talk about how we went through each layers of this technology stack to do fuzzing and a little bit of code auditing and talk about some bugs that we found. And then I'll just leave with some concluding thoughts on where I think this technology is going and what it means for everybody in the room. So what is eBPF? It's the virtual CPU architecture. So this is a non-existent CPU. It's a software CPU, much like a JavaScript engine or some other emulated CPU. And it was originally designed to do network packet filtering as part of the Berkeley packet filters in Linux. And it's designed basically as a more general purpose extension execution environment for kernel modules. So this is a way to run code in the kernel on a virtual CPU that's sandboxed. The way that you create a program to do this is you write it in standard C language and you include some special headers. And then you can use LLVM to compile that to this custom architecture. From there, you can use traditionally system calls on the Linux side to load these programs into the kernel context and implement hooks into the network layers or into code instrumentation callbacks. In general, the system is designed for high-speed inspection and modification of network packets, and also the ability to hook both userland and kernel functions. So this all started back in 1992 when BPF was added to the Linux kernel, and this is a precursor technology in these days, and it was specifically designed to filter network packets. So if you've ever used TCP dump or Wireshark and you've used a string to specify a network filter on a certain IP in a port, you are in fact interfacing with the BPF implementation inside your kernel. Those strings, those filter strings, behind the scenes get compiled into a BPF program on the fly, and that code is then JITted into the kernel, and these hooks are implemented in a high performance manner in that way. So we call this old BPF implementation that was specifically for doing network filtering the classic BPF. Now, as of about 8 years ago, Linux kernel 3.18 released a new version of this that extended the concept of the BPF packet filter to a general purpose execution environment. They went from having 32-bit instructions to 64-bit instructions. They added the ability to use persistent data structures. So your BPF programs could store arrays or linked lists or hash tables of information as your hooks are monitoring network traffic or functions getting executed. Then this extension allows you to store that data across different invocations of your eBPF programs. On the right-hand side, some of these screenshots in here I know are not the largest. It's okay. We have a ton of slides, so this is going to be a pretty quick talk or paced talk, and there's a lot of extra info in there for you to study on your own. But in the Linux side, it is all implemented through a single system call interface. And inside that system call, there are a bunch of sub-operations and sub-features. It's kind of designed in the way that a device ioctl might work, where you have a number of commands hidden behind a single kernel interface. One thing about eBPF that's unique is that it implements a static verifier for these programs. So because you're able to load code into the kernel, they wanted to add some security guarantees. So there is not only the virtual CPU execution environment, but also a On the Linux side, a fairly simple static analysis pass that tries to ensure that memory safety and the programs will terminate within a short amount of time. In general, applications of eBPF are for network instrumentation, load balancing, monitoring, telemetry, things along those lines. And at this point, the environment's fairly mature on the Linux side. There are Go and Rust and Python and C backends that all interface with this. And at the end of the day, they still all call into that system call. And the layout is basically everything happens in the kernel as far as Linux goes. If you use any of these products on Linux, then you are already using the eBPF infrastructure, things like Microsoft Defender for endpoints or Cilium for Kubernetes, things like that. So the last few years at Black Hat, we've also seen a few talks about the Linux eBPF implementation, focusing on red team applications. And I myself just gave a talk a couple of weeks ago at TourCamp and last fall at TourCon that talked about basically writing rootkit, attack and defense, but kind of a tripwire style whitelisting for binary execution, as well as the ability to inject code into executables as they launch. So switching focus to the Windows timeline, basically, we saw it was, 2014 is when it was added to the Linux kernel. As of last year, in May, Microsoft announced their intent to bring this platform to the Windows side of the house. Now, of course, we all know that Linux is GPL kernel, and Windows, of course, cannot adopt that code directly into their kernel, so they had to come up with a way to re-implement the entire technology stack. And so that's kind of why this is interesting. It's a net new set of code that implements something that we've seen grow and become adopted heavily on the Linux side, and is really all indications point to this being the general platform for the future for doing telemetry. So in 2021, Microsoft announced that they had implemented 2 network hooks that can be interfaced with through eBPF programs. You use the exact same compiler stack, you use LLVM, you output the exact same bytecode for this virtual CPU. Internally, it's all similar. The differences, of course, are how Microsoft re-implemented these interfaces and plugged them into the kernel. So in August, they announced that they had matured some of that code and added, or I guess it was closer to November, but they had added about 68 APIs that are part of the standard Linux API set for doing eBPF instrumentation. And as of this February, they released kind of their first functioning implementation of a program that runs on top of the Windows eBPF stack, and that was the Cilium Layer 4 load balancer. So as of this February, from last May until this February, they've more or less implemented a bare minimum, minimum viable product for doing eBPF. And that was about the time, of course, that the Black Hat's CFP was around, and I'd already done some research into this, so I figured we would continue down that path and see what kind of security architecture is there and what exposure is there for attackers. So on Linux, as I said, it's all in the kernel. On Windows, we see this diagram on the right. It comes from the Windows eBPF project, and it shows that basically we have several different components, both in user land and kernel, orchestrating together to create this overall system. And in particular, Microsoft adopted 2 open source projects that are BSD licensed, the IOVisor uBPF implementation, which that's the virtual CPU, and the Prevail static verifier, which was an academic work that tried to enhance the security guarantees around the static analysis engine. And I'm going to dive into each of these components. You'll see them blown up, and so here we go. The current implementation, so on Linux you can hook, as I mentioned, functions and userland and kernel, as well as do network instrumentation. On Windows, so far they've only focused on the network stack. So right now they're interested in using eBPF in places like the cloud space to do virtual networking, to do load balancing, to rewrite packets on the fly and distribute them to other systems, things like that. It is shipped as a standalone component, and in conversation with Microsoft, they've indicated that this shipping model is designed so that when you write these programs, which effectively are kernel modules, you don't need to go through the standard driver signing and driver verification process that you do with Windows. And so you have a much faster serviceability model, which is one advantage to this. And because everything here is MIT licensed, it can also be consumed by third-party products and shipped as a component of an overall system, such as an XDR or EDR platform. On Windows, it works, as I said, just the same way. You use Clang, LLVM backend, you write a simple hello world style program. There's some special APIs that allow you to do things like print to the screen or to logs. And you'll see there's this annotation here that shows SEC bind. What's really happening is that's indicating that we're going to add a special section to the ELF file that is going to contain this particular function. Now, BPF programs themselves are one function long, but they do have the ability to call into each other. So if you compile that hello world, you'll see that an ELF file is generated, and in the text segment, there's actually no bytes, size 0. But there is a new segment called bind, and that is hex 68 bytes. And so that was where our compiled program was put. And you can also use LLVM objdump to inspect that section, and you'll see this virtual CPU representation of instructions down there on the bottom right. For later reference, if you look at these slides, here's a couple screenshots of a full program, and it shows that there's multiple sections in here, some of them holding these data structure maps and other ones doing things like network packet inspection. So the different types of programs, or eBPF programs that you can implement, correspond to the types of hooks that you want to leverage. And so at the lowest layer of network stack, there is something called XDP. And this is a layer that actually is coming directly out of your network driver and before it really reaches the rest of the Windows kernel. And so if you implement an eBPF program at the XDP layer, you're actually able to rewrite packets and resend them out of the box before they're ever technically received by the OS itself. Very fascinating stuff. Bind is a type of program that allows you to respond to port binding and accept and general listen and those types of APIs. And then there's a handful of C group related and SOC operations related hooks that you can implement as well. Again, this is just for a visual to show you that there's a set of APIs. We don't need to talk about them specifically, but these APIs allow you to do things like interact with the maps, create the maps, pull data, store data, call other programs, things like that, figure out what CPU you're running on or what thread you're on, and you will use this to also interact with other kernel APIs, perhaps. So ultimately, what's the security model around eBPF for Windows? Well, it's allowing us to run unsigned code in the kernel, right? So any break in the security model or implementation here is going to be a driver signing enforcement bypass because we're already getting our code into the kernel, and if the security guarantees are not valid and we're able to break them, then of course that means that we're getting native code execution in the kernel. Now, the implementation of Windows eBPF, we're very early on the curve here. As I mentioned, there's no function pointer hooks, and there's just basic networking. And because of that, the DACLs that are on access to the kernel object or to the APIs themselves through RPC are restricted to administrator. So ultimately, we'll talk about kind of what the attack objectives would be, but we have to keep in mind that you have to be administrator to interface with this subsystem currently, and therefore the attack model is going to be something that more or less is, kernel. As an administrator, we can already read memory from the kernel. So really what we're looking for is the ability to write out of bounds or to get full code execution. And so of course, the bytecode that is generated by LLVM is then loaded by the static verifier, and we'll make sure that it's not violating those security guarantees. I should mention on the Linux side, there is a part of this attack surface that is available to unprivileged users. And so you don't always need to be root to call the BPF system call. And in the source code of the Windows implementation, they do have comments in there that indicates that in the future, some of these APIs will be opened up to standard users. So Prevail is the name of that static verifier, as I said, and it's using abstract interpretation so that it can do things like pointer analysis and check that you have, if you have a pointer return from an API, you have to check it for null before you can actually dereference it. It has all these built-in analyses, which are much more sound than what is in the Linux kernel in theory. Also, in eBPF, as opposed to the classic implementation, we can do things like actually implement loops and tail calls into other eBPF programs. And as I mentioned, this is all net new code using IOVisor's eBPF stack. Interesting thing about eBPF is that it can run both in userland and kernel contexts. The U stands for user mode. Or user space. And what this also means is that we can leverage this virtual CPU in other contexts than just the eBPF stack. So in this case, we're plugging it into the kernel to do network introspection. In other cases, it may become a replacement for Lua or V8 or JavaScript engines in general in other places. So it's in general a really interesting platform to consider. All right, so what are these security guarantees that this all ties together? Well, number one, because these are meant to be high-performance filter hooks, they have a limit of 4096 instructions that can be in a single function. And so the static analysis is able to, in fact, unroll loops and ensure that you will terminate the old halting problem, but since they have restrictions on the execution, they're able to prove that it will, in fact, terminate. And as I mentioned, it tries to ensure that your pointers, when you dereference them, are pointing within bounds of buffers that you control and have permissions to access, and that you're doing basic checks on return values. Also, that your stack pointer is within bounds. There's a dedicated chunk of memory for your VM to be executing in, all these sorts of things. And in fact, as we'll see in a moment, the service itself can be run in a hypervisor code integrity mode in the future. It's kind of in progress. So the attacks that we're looking for, since we are administrator, is that we would like to get code execution as admin. And the first way that you could do that is if you load a security module or eBPF module that comes from a third-party project, because you want to collect telemetry on your system. And so you go off to GitHub and you download and compile eBPF program. And that's one attack where you would get user mode administrator privileges. Then there is the trusted service, which exposes an RPC endpoint. And this is a PPL process, so it's highly privileged. It's considered part of your trusted computing base. And so any vulnerability there is the equivalent of having direct write access to the kernel. Then, of course, there's the static verifier or the JIT engine itself. If either of those, as they process the code, read out of bounds or write out of bounds, that would be a vulnerability. As well as there's an interpreter mode, so same idea there. And then there's a whole ioctl layer, which, of course, comes with its own implementations of handling each ioctl request before it interfaces with the eBPF subsystem itself. And then finally, these hooks that exist that hook into the network packet layer themselves, these are grabbing packets and preparing them into data structures that the eBPF platform can access. And so there's some memory management happening there where those hooks themselves could be exposed to potential remote over-the-wire network packet attacks. So, and I am going to try to go as quick as possible here, but the first component that we're interested in is the userland API set, and that is contained in the eBPF API.dll. And basically, this is where the userland user, administrator, will be able to load BPF programs, unload, get a list of what's loaded, add maps, kind of interrogate the system in general. It's the equivalent of executing the system calls directly. And it does come with two tools that you would interface with. One is a standalone tool called BPF tool, and another is a plugin to the NetShell Windows kind of WMI backend. So what we want to do is fuzz each of these layers directly, and in order to fuzz the API layer, we know that the entry point to interacting with that is basically to give it an ELF file that Clang emitted, or to give it a raw stream of bytecodes, and then that will pass it to the verifier. So we ended up fuzzing this 2 different ways. I actually fuzzed the Prevail and eBPF independently quite a while ago, and found some crashes. So we did some cross-fuzzing there, where we just took the output of fuzzing these components independently on Linux and then ran them through these loader tools on Windows. And so we'll talk a little bit more about the bugs that we found in the individual components, but the first big vuln that I found was as a result of this approach, and it hits that very first attack goal, which is we found a vulnerability that gives you remote code execution or arbitrary code execution through the loading of an ELF file that contains this eBPF bytecode. So this particular vulnerability results in heap corruption, which calls free on a user-controlled pointer. And if an administrator were to load your filter, then you get remote code execution on that box as admin. The output shown below here is showing the Windows debug verifier, showing that there was a corrupted suffix pattern on a heap block. And if we look at the location that it says the corruption address is at, we see that there's 4 A's that I've conveniently placed there to show you that, it's hacked. So this attack would ultimately allow you to control a free pointer, which isn't typically a exploitable scenario if you have enough control of memory. And here's a little call stack that shows how we got there. The way that this was doing the free, it was in the destructor for an eBPF program, and it was dealing with an array of eBPF instructions. So it's just trying to free all the objects that represent the instructions. And the way that that allocation occurred that was missized was due to the processing of relocation entries in the ELF file itself. So you generate an eBPF program, an ELF file, there's a relocation section, and as that gets parsed, it's being done in a loop. And because this is an ELF file, you have the ability to require segments and sections to be loaded at kind of arbitrary places in memory. You have a high degree of control of memory, and you also have a looping construct as it's parsing through these different sections. You can, of course, have multiple sections, as many sections as you need. And so the combination of having a good degree of memory control and a looping-based parser means that I didn't have time to fully exploit this myself in the time that we had allowed, but it definitely would be an exploitable class bug. So moving past the user mode API, the next layer is that service, the PPL process. And this is, as you see in the blown up diagram here, primarily all this actually is it implements one RPC endpoint, one API that you can call. And that API simply says verify and load program. And you pass it the data structure that has been generated by that first DLL that has pulled the bytecodes out of the ELF file and now has prepared an array or data structure that holds the instructions and passes that over. And the attack surface that should be available here is the Prevail verifier and then ultimately the JIT compilation that happens after verification succeeds. And if you get in there, the API is quite layered, and so there's several API calls that kind of get you to this same point, whether you're using the DLL or the RPC API, they all kind of get to the same API call. And so when we were fuzzing the DLL, we were also actually already fuzzing through the RPC endpoint. We did try to, oh, sorry, before I get there. So we did fuzz these components individually, of course. So Prevail verifier and eBPF. So the Prevail verifier, you can go look up the paper. It's a polynomial runtime eBPF verifier using abstract interpretation layer. All that really means is they're using a lot of math to try to do this pointer analysis. And it can be used anywhere that eBPF can conveniently. It comes with a standalone verifier tool, and so this, of course, was the tool that we harnessed, and this is very simple and straightforward. It takes a file input, so we can use our trusty AFL++ to do that fuzzing. So I did this fuzzing actually last fall, prior to my TourCon talk, independently when I was looking at the Linux side of eBPF. And so here on the screenshot, you can see that it found some crashes. When we run those crashes through a tool called AFL Collect, again, I realize it's kind of small, you can look later, but this first screenshot shows that we have found 303 crash samples, and what I noticed in here is that some of these are handled aborts, they're doing asserts that lead to aborts. So I filtered those out, and then we're down to 56 unique crash samples, and we do see the red lines that we see here are basically Bang exploitables saying that this is likely an exploitable crash. And here's a couple pages of crashes, right? So I knew going into this project that the verifier itself had some vulnerabilities in there. A blown up screenshot of what one of those bugs was. It was indicated as probably exploitable. In fact, in this particular case, it was not really exploitable. It thought that it was a memory write, but it's actually on the test instruction, so it's dereferencing a value. Turns out to be a read AV, not too crazy. Well, so we had this pile of crashes though, and we knew that we wanted to run them through the Windows side is kind of the idea. Same thing on the eBPF side. eBPF can run in an interpreted mode or in a JIT mode. So ultimately, this eBPF does not implement any of the maps or any of the helper functions. It's just a pure virtual CPU. So really, we're just trying to execute out of bounds or read or write out of bounds of the virtual CPU environment. And so if we fuzz the interpreted mode, found some crashes. Again, AFL Collect shows us these red lines that say there's exploitable bugs there. And in the JIT mode, it got even crazier, all kinds of exploitable crashes. But as it turns out, the heuristics around this weren't that great. And so at the time that we found all these bugs, I didn't submit them all to these open source projects because A, I didn't know that these were going to eventually make their way into Windows yet, but B, because a lot of these were low grade, issues that ultimately I was waiting for a more significant project to use this CPU in a meaningful context. And so we had all these bugs, and just kind of knew that we would want to follow up. Now here, this is one that we did find and replicate in the kernel side. This one is showing a vulnerability in the eBPF destroy, where it is freeing the virtual machine as it's trying to terminate the program. And in this case, the pointer was corrupted. So these components are sitting inside this eBPF service DLL, and we fuzz that both with WTF, but actually once we got to this component, Microsoft started doing their own fuzzing sometime in June, late May, June, and ultimately the bugs weren't reachable or they were already patched, and so the eBPF service itself, the PPL service, turned out fairly clean as far as exploitable bugs go. So then the last area that we wanted to switch to is, of course, discovering what this kernel driver exposes, because that's really where everything's going to end up eventually. And of course, it exposes a nice ioctl interface. And as I mentioned before, the DACL on this device object does require administrative privileges. So we are looking for unsigned code execution, ideally. The interfaces that are exposed through ioctl allow you to, resolve functions and maps and load programs, get the next program ID, interact with ring buffers and data structures and all these sorts of things. Plenty of interesting memory modification going on there. And so this is kind of where the majority of the attack surface that became interesting existed. And because it's in the kernel context, we can't use simple AFL style approach or cross-fuzzing really. We needed to come up with another approach. And so in this case, we leveraged the tool called WTF Fuzzer from Axel Souchet that was released last year, also known as Overclock. And the way that this fuzzer works is we take a snapshot of the complete operating system memory from the kernel debugger, and we write that to disk. And then there's a component using the box CPU emulator, x86 emulator, 64-bit. And it's an emulation-based snapshot fuzzer. And ultimately, this allows us to set a breakpoint at the entry point to any function we want, whether it's userland or kernel, and replace the contents of buffers being passed to those APIs to do our fuzzing. Other advantage of this is that it is distributed, so you run one server and it uses TCP sockets and communicates over the wire from clients. To implement a harness, you more or less just need to write 3 functions. One that inserts the test case and moves the newly fuzzed data into the buffer that is in the memory snapshot, and then some initialization for catching calls to swap context or other functions that you would either want to modify or you would just want to force terminate your fuzzing session. Due to time constraints, this is just kind of an introduction to the WTF as being a powerful tool for doing kernel fuzzing. You'll have to go look a little bit further on your own. But ultimately, it comes with a demonstration fuzzer that is able to do type length value network fuzzing using multiple packets. So we forked that, modified it so that instead of hooking the network sockets, we hooked below the device IO control file API. And you'll see in the call stack here that ultimately from the userland, where you would normally call device IO control, it passes through several layers until you get to the kernel side handler for all of that. And we replace the contents of those buffers each iteration. And then we had to use a JSON-based serialization format that could hold multiple ioctl requests. So our whole goal here is to be able to send, a dozen ioctls at once that kind of manipulate the same maps or programs, looking for various vulnerability classes. And so ultimately, we serialize the contents of what the ioctl data buffer would be and add a little bit of metadata around that in order to re-execute those, or to inject that data properly from our WTF hooks. So when you run WTF client, it looks something like this. And if we have time, I will do a live demo. But basically, this is showing a client booting up and outputting occasional updates. On the left-hand side is the iteration number and how many blocks it's covered and how many executions it's getting a second. Now, the executions a second here per client is quite low. It's only in 15 to 20 kind of executions a second, but that's because we're sending up to 10 ioctl requests at once. So we're activating a lot of behavior inside the kernel. If you only do one, it can be up to 10 times faster, basically. And of course, we can scale this across many CPUs. So we were ultimately using like 40 cores and getting 300 executions a second or something. On the server side, when you initialize it, it boots up and shows you that it's starting to receive information from the clients. And ultimately, we're looking for outputs that are being saved as crashes that we can then go replay and test. So the results of our kernel driver fuzzing did come up with a handful of crashes. Unfortunately, most of these are robustness kind of layer crashes because you're already administrator. So we did get out of bounds read access violation, which of course tears down the system and causes kernel to panic. But at the end of the day, you're already administrator, so technically you could probably shut down the system if you want to. But here's the call stack for that. As I mentioned, the eBPF core invoke protocol handler, I believe that's where we were squirting in our data. There was another one. This is the eBPF destroy API. It's the same bug that I mentioned I found in the userland side, but here it exists in the kernel because the kernel has the JIT engine inside of it, or it has the interpreter inside of it, rather. And so that same code is both present in userland and kernel. And so depending on how you interface with the APIs, you can trigger those bugs either in userland or in the kernel. And then yet another crash and trampoline table, and so on and so forth. So overall, our goal here was, A, if we could find exploitable bugs, then great. And we did, and that first vulnerability would give you administrator access. And then we wanted to just continue to do robustness testing and an overall deep dive into the security design here to get a sniff test of, how how well has this code been fuzzed or checked, done security reviews. And it is a moving code base, it is a young code base. So we did expect that there would be various problems like this. It's not unexpected. And as I said, Microsoft has begun fuzzing sometime in late May and in June, and they're very rapidly fixing a lot of these bugs. So some of these we didn't bother submitting, just because they're read AVs and null dereferences. If you're wondering what the output of the fuzzer looks like, where it has multiple packets, here's a little screenshot that shows what that JSON format looks like when it actually contains a number of requests. And then also to continue our fuzzing, we wanted to experiment with AFL NIX, which is American Fuzzy Lop plugin that interfaces with a hypervisor-based snapshot fuzzer called NIX, or KAFL, it was previously called. And but because we spent about a month or at least 3 weeks fuzzing before we really started switching to NIX, we didn't find any new bugs, but of course we did still find similar bugs to the ones that we had found before. And we weren't reusing the harnesses or crashes or anything. It was going from the same template. So one thing to notice about this is that a single core was getting 65 executions a second instead of just 15 or 20. And so we do see that NIX is substantially faster. It's just a little bit more difficult to set up and scale. So that leaves the last bit of attack surface, which are these kernel extension modules, and the network hooks are implemented in a kernel extension module, and in the future there should be something that implements detours or code hooks in a different extension module. The network one is called net eBPF extension, and this one was small but a bit complicated to fuzz because, as I mentioned, this is going to be what reads the packets off of the wire and implements the hooks that will pass the data to your eBPF program. And so we're interested in just that little chunk of code that does that translation. And so in this case, we actually did a code audit. Both myself and Andrea just read the code. There wasn't a lot of memory management happening. It does a lot of zero copy, just pointing at things. And so we didn't come up with any new bugs there. Lastly, as I said, the code hooks will be implemented in their own extension modules. So that will be a thing for the future. And really quick, because we do have 2 minutes, and that should be just enough time to do the live demo. If I switch here. Okay, so this is going to just be a demo showing us running the WTF fuzzer and finding bugs in real time. In this directory, this is the WTF directory. I have a bunch of metadata there, so we're going to delete all the crashes and the inputs and the outputs from the previous run. I'm going to dump the list of JSON packet harnesses that we've created, and then we're just going to copy one over, just the create program JSON. So what we're seeing here, though, is that these were all ioctls that we created a plain structure to feed into the fuzzer so that it would do these individual requests, and then those get mutated over time and expanded and modified to find the crashes. And so lastly, I'm just going to tell it to quickly launch a screen session, which will have 8 clients connecting back to the server, fuzzing our ioctls. We will not copy the previous inputs. This is showing it booting up an HTOP, so I'll exit out of that. We will okay, and so what we're seeing here is that, in fact, I started this run in the speaker room, so this is the wrong screen. But what we see here is that it has been running for a little while, and we've got 8 nodes connected. We're getting 100 executions, or I'm sorry, 16 nodes now, 100 executions a second, and it has found 20,000 crashes since a couple hours ago. So concluding thoughts. Sorry, we're on the last minute here, but in general, eBPF is an exciting technology. It's going to be the underpinning of telemetry now and in the future. It's coming to Windows. Windows will be able to run the exact same eBPF programs. They're portable, and Microsoft has joined the eBPF Foundation, which is part of the Linux Foundation. And so there's a lot of weight behind it. So did Netflix and a few other cloud players. And we found one serious vulnerability, found a handful of robustness vulnerabilities, applied fuzzing at various different layers. And ultimately, we're here as Trellix to do proactive research on security for the public and for the future. So thank you very much for attending my talk. And yeah.